So why were we fooled here? As we said, that's because of hidden factor. Here we have something that we can call a nuisance factor that has some impact, sometimes less, but sometimes even more than the desired factor. And the bad news is the nuisance factors, unless you work hard on it, they will exist. So if you can do a performance analysis of something, then you will have your paper rejected because people will say, oh, it's very easy for a reviewer to look for nuisance factors, and if you have not properly designed your experiments, they might well be present. Second thing we did is to interpret correlation as causality. We saw when, or you did not, because in the poll you said, no, I don't believe that mobility increases capacity. But we might conclude that, and that would be also a lack of scientific methods. Let's go even one step further, and there's a well-known paradox, which is called a Simpson's inversion, or Simpson's paradox, which came in a different setting, but I'll explain it here. If I consider that I'm interested in the throughput I require for this application is a fast download, and I want at least 1.5 megabit per second. And I'll say that my experiment succeeds if I obtain this throughput. So if I look at my devices that were slow, I said those were the pedestrians, which are less than this speed here. Here is the statistic we get. Right? Out of the slow mobiles, we see that 11 out of 14 succeeded. Out of the fast mobile, only 3 out of 11 succeeded, but for the fast, 4 out of 9 here. So we see the probability of success doubles when we are fast. That's a 1-bit quantized version of the linear regression I did before. But if I see only this information, I can conclude that mobiles that are fast have a higher chance of success, of providing the good service we want. But, as you can expect, if we reveal the hidden factor and we redo the probabilities, we find something different. We find the probability of success given slow and given small buffer size is those values, very small, whereas given large socket buffer size, they are those values that are very small. And the ratio, the relationship is inverted. When you're slow, you have a larger probability than when you are small. This is called Simpson's inversion. We have a certain probability or a performance metric that depends on one factor, slow versus fast, in a certain monotonic way, when we do it by revealing all the hidden factors. So I look at the marginal dependency of the final thing I'm measuring here with respect to my factor of interest for each of the possible cases of the other factor. And I find it's increasing. When I integrate everything and I take the non-marginal but the global dependency, we see that we can have the reversion here. This is smaller than that, whereas in the other case, it's the other way around. The first time this was published was for a slightly different setting. It was admission to graduate school in Berkeley, and a feminist association sued Berkeley University by claiming that they were discriminating against women. And they based that on global admission cases here. Out of that many men applicants, 40% were admitted, and only 35% of women were admitted. But fortunately, the lawyers, this is the US, so in the US the lawyers spend huge resources on studying things, plus this is against the University of Berkeley, so you have people like me there who are trying to defend the university. In that case, the university was not guilty, because what happens is that women apply majoritarily to departments that are very selective, where there's few slots for a huge number of applicants, life sciences and medical school, as opposed to engineering, which is much less competitive because most people don't want to go there. They anticipate that it's hard and very complicated. So this is exactly what has happened. If we reveal now the hidden factor, which is the major, so the department that have been anonymized here, we see that the applications, in fact, are the performance are practically the same for those departments here, and marginally better for this department here. So you cannot make the case that there would be discrimination against gender in this case here. But what happens, of course, is that you see that A is probably engineering, where the admittance rate is very high, but the number of men that applied is also much larger. The hidden factor was explaining that. Women got less accepted because they were applying in large numbers to departments that rejected a lot. So if there is a bias, it is in the choice of department, but not in the selection procedure. That's exactly the same thing as with our mobile. With our mobiles, the hidden factor was the socket buffer size, and the desired factor was the speed. Here we have exactly the same. So the take-home message, let's dissect it a bit to understand how we can avoid it, because that's also one of the goals in particular, if we're able to design experiments. I'll do it for the two-factor good versus bad. So good means the throughput was large enough, and whether it was slow or fast. And there's a hidden factor, which is here the socket buffer size. Then I'm writing here a formula in probability, which is called formula of total probabilities. That says that the probability of something, of good, so good, this bar means given slow. So probability of good given slow is the probability of an experiment returning a good result, given that it was performed under the slow conditions. So we can ignore the given slow for a second. This is the probability of good. Then the law of total probability says if I can condition that on the value of the hidden factor, I have this formula. Probability of good is the sum of probability of good given that the hidden factor is I, multiplied by the probability that the given factor is I. So you should recognize one of your preferred probability formula. If not, then it's time to learn it. If you ignore the given slow, that's called the total probability formula, and it's intuitively very simple. Just common sense. And what can happen is, of course, that we've seen that this is larger than that, but since we do a weighted sum of those probabilities here, which are, if you want, our metric, it is possible that by weighting things that are in a given order, we obtain something that is not in the same order. So by summarizing and aggregating things, we can reverse the order. This can happen, as we have seen, if some of the values here are very small and the weights are very large. For example, here. For example, when the probability of being rejected as a woman is very large, when you apply to a department that has a large number. So since the weights are different, it can happen that there is this inversion. If we want to avoid the inversion, then we should make the weights equal. If we have the ability to design the experiment, of course in the case of Berkeley's admission, we can't design it. But in the case of my mobile that is moving, you have two types of mobiles, and one phone that for some reason is configured in some way, another phone that's configured in another way. The best would be to configure both the same way, but perhaps I can't because they don't have the same version of Nougat or Vanilla or whatever operating system. So if I can't, then what we need to avoid this inversion is to do a proper randomization. And what does a proper randomization mean? This is what we will discuss now. If we look at this formula, one way is to make the weights equal. Weights equal means the probability of the hidden factor being I, given another factor of interest as this value, should be the same as that here. What does that mean, in fact? In more usual terminology, the equality of those weights. Is this related or not to something called independence or uniformity or whatever. The majority says says B, but the correct answer is A. But admittedly, it's tricky, but this is very important because this is about what we call independence, which is invariably used everywhere in statistics, probability, data science. We always assume some things are independent. Even if we don't say it explicitly, it's very often done implicitly. So we need to spend a few minutes knowing what exactly independence means. So independence, when you take a first course in probability, means this. Two random variables, x and y, are independent if the probability of x taking the value I and y taking the value j is the product of the marginal probabilities. And that must be true for all possible outcomes of x and y. If the random variables are continuous, you have slightly different definitions, but here I take discrete random variables to make the story not unnecessarily complex. Now, another thing which is less well known, but is in fact more useful, if you compute the conditional probability P of x equal I given y is equal to j, is the probability of this divided by the probability of that. So this should be equal to the probability of x equal I. Right. You can even see that the simple fact that this probability here does not depend on j, because the sum of the probabilities must be equal to 1, means it must be equal to that probability. So a weaker form of this, which is strictly equivalent to that, is this. Saying that x and y are independent is saying the probability that x takes the value I, when I have observed that y has been revealed to me, I know y is j. If I look at all the experiments where y had the value j, what can I say about x? Well, if the answer is, well, what you can say about x does not depend on j. Right? So having revealed to you that y is equal to j does not give you more information about x. You don't know more where x will be. That is independence. Independence means exactly that. It means having observed y doesn't give me any information on x. Given that x and y satisfy a certain law of probability or follow some distribution here. So if we go back to our quiz here, that means exactly independence. Given that we observe slow, or given that we observe fast, the probability of the hidden factor taking a given value must be the same, regardless of slow or fast. That means exactly independence of the hidden factor against the factor slow/fast. Now, whether things would be uniform is not the same thing here. Uniform would mean that the hidden factors themselves take the same are distributed uniformly. The probability that the hidden factor is small versus large is the same. But that is not the same thing as independence. The key thing for avoiding undue bias, Simpson's inversion in particular, is to have the hidden factors independent. So we want to design, if we're able to design here, we have to randomize the experiment so that the hidden factor is independent of the desired factor here. So for example, if we are forced to use the two types of devices to do the experiment, and when we do an experiment, we can say, I'll pick randomly one of the mobiles, and I will redo the choice independently of the experiment I am doing. So take-home message, the bad news is the hidden factors, they are not given by science, they are just given by expert knowledge of the system. So you have to imagine, based on the knowledge that you have, what are the factors that might influence the outcome. If there is a hidden factor that nobody discovered, then something that was believed true might become untrue. And that happens in medical sciences. We discover that medicine that was deemed to be good 20 years ago is proven to be bad now because we have discovered a hidden factor that was never discovered before, right? So this risk is always on us, except when we work with artificial devices, systems that we build or where we make simulations of. We usually have much more freedom to design the experiments. Especially if we do simulations, we can screen all the results that might have an impact. For example, when you evaluate Linux versus Windows, what could be the hidden factors that can easily be avoided? Well, if you have Dropbox on your machine or not, right? The Dropbox will generate a lot of background traffic, so the network will create a lot of background traffic. That might easily use a lot of the resources, so there might be a number of hidden tasks that are consuming jobs. By default configuration, it might be present in Windows and not in Linux, and if you disable them, because Linux is typically much less feature-rich by default, you need to add the things yourself, so that would be, for example, one of the hidden factors. Thank you. So in the paper that I give as a reference, they try to screen all the hidden factors, and for example, they perform the experiments while disabling the network. One radical solution. So we mentioned if you can do experimental design yourself, then try to randomize the experiments by making all the hidden factors that you've identified, but you cannot prevent them from being present, and make them independent of the other. We will see another technique which consists in making them appear explicitly in the analysis when we'll talk about model fitting. If we can fit a model that has all the factors we're aware of, then we can look at the marginal dependency on the factors of interest. And this is what we did, for example, when we did the linear regression of the TCP throughput as a version of speed. We had two different lines depending on the type of mobile. It was small or large socket buffer. That is another technique that is also possible, but of course will require more complex things. So this is the first part that I'm almost finished here. I'll talk about bottlenecks and patterns in a second. But the most important thing is perhaps this one about our first grasp at statistics. We'll come back to statistics a bit later here. And if we put all this together, then we have this. Those are the things. What do I want to do? What do I want to measure? What's the load? That's typical of computer systems. And what we have discussed, what are the factors? Here is back to one of the points we have discussed a bit last hour. Here is an example of a measurement that is performed in a wireless shop. So Joe sells online content. In fact, in a museum, he sells, visit the museum, and then you have to download the online content from a booth there. And he measured the number of transactions per second, so how many people, in fact, are at the booth, versus what is the throughput achieved by his server. And here is the plot he obtained here. So we see that it increases as more and more load is present, and then it flattens or sometimes even decreases here. Yes, those are not points, but the drawing here. So we see it looks like it perhaps has a performance problem here. You are the performance analyst. What do you recommend to Joe? Well, there's no correct answer. We find a whole spectrum of possible answers, which is perhaps showing that you are right, because of course we cannot really decide at this point. But very often people will still try to decide. So what Joe did is to buy 2 more access points, Wi-Fi access points, where people come and this was the same as before. I changed the scale a bit, so it's not a little bit different. And after, of course, the points are a bit different because we do a different measurement. But as we see, there's no real improvement here. So we have simply bought more hardware, but the problem did not go away. Why was that? Can you imagine why? Exactly. There is a bottleneck here. There was something that was limiting the performance. It was not the wireless access point. Perhaps the server right here. So what Joe did is jump into a conclusion like we discussed before, and that we should not do that. Oops, sorry. But the scientific method, which is what people do in physics and life sciences, and when we want to say something about the performance of a system, even if it's an engineering artifact, is summarized in these 2 lines of code: do, define hypothesis, design experiments, validate until validation is okay. And typically when you do an experiment, you have to expect that there will be iterations. So when you will do your mini project, you should not expect that I will do this, the first week I will write the code, the second week I will run the experiment, the third week I'll do the statistical analysis, and the fourth week I'll write the slides. That won't work. It's like in software design. You will do things, look at what you have. This will tell you things that you will use as hypotheses that might lead you to define new experiments, do new simulations where you measure something else, where you vary another factor, which will again tell you something until you reach a fixed point where this doesn't tell you anything. That is the scientific method. This is how science has been done. This is why we have things that everybody believes in, like the laws of gravity or classical mechanics. Before that, there was lots of fantasy theories, and in modern physics, there are lots of things that are still in the middle of the loop. So as you know, modern physics is still ongoing work. So there are experiments that people do that invalidate things that thought before. So they do new experiments, and this is why we have lots of physicists in Epfl and other places. We're busy doing that. We're not as expensive as physicists. We do things that are much faster, but we will expect this here. Back to Joe. Joe assumed the wireless network is the bottleneck. Before buying his 2 access points, what Joe should have done is measure the number of, try to validate this hypothesis. For example, by measuring more in detail the performance of the access point, of something that would indicate the saturation of the access point here. So he found, for example, a small number of collisions. Collisions are always present in CSMA-CD, the CSCA, the protocol of Wi-Fi, but a number like this indicates there is no congestion here. So it was not the access point, so we can try another thing. For example, that the server is saturated. By looking at one of the memory caches of the server, and if he's able to get the logs and statistics, you can see that this was indeed the bottleneck. So either you buy a second server, or you buy another processor that has larger memory cache, which is what Joe had after buying multiple servers. Voilà, so that's the first thing. So in summary, first thing we've seen is that when we do metrics, when we measure a thing, we have to be aware of the hidden paradox, of the hidden factors. If there are hidden factors that have a non-negligible impact on the performance, our conclusions might be completely off. Simpson's inversion, Simpson's paradox. Second thing, once you should expect that the method will be iterative. By looking at the curves and the result of an experiment, you should not jump into conclusion. You should pose the conclusion, then wait for a second and think about whether there might be other reasons for what you see, and then how can you find out among all the possible explanations what is the one that is truly the correct. So that's the bad side of things. Now let's go to the good side of things, is trying to find patterns. There are things that are very common and that can very quickly give us ideas of what are the most likely hypotheses that we want to make. It's like in a thriller. If you want to find who is the murderer, you look first by Bayesian probabilities. You look who are the most likely murderers. For example, when a woman is assassinated, usually it's the husband or the lover. So we'll try those guys first, right? And if you can find proofs that those guys did it, that's the end of it. You've saved a lot of time. Same story. Patterns are things that happen very often, so they are very logical first guess, first hypothesis that we can make. Of course, you should not stop there. You shouldn't say because it's the most plausible, he must be the murderer. No, he might be wrong. The first one is bottleneck here. We have discussed already that with the one thing here. So here's, for example, some people are trying to evaluate the performance of an information system that were compiled with two different systems, A and B, and then you evaluate the performance with users that are remote on the internet or local in the testing environment, and you look at the performance in access time here, so the time to complete a complex transaction on different days here, and we find those different values here. The expert concluded that the performance for remote users is independent of the choice of an information system, but for local users it's much better with A, which is what we see here. But if we want to go beyond, what could we say? Well, we could say that perhaps here there's one thing which is not the information system itself, but the bottleneck. Perhaps the network access is poor, or there is a firewall or a VPN or something that is throttling the performance. And then whatever you do A and B, what dictates your performance is whether if you're remote, is this other system. So by doing that, if this is true, then there's no point doing that here. And perhaps what you should do before deciding between A and B is get rid of this bottleneck that is on the remote access. So bottlenecks are like nuisance factors. They impose their agenda. But sometimes that can help us. Here's another example. People have measured a transaction system, and they've found that one transaction costs that million CPU instruction, 100 disk access, and 4 packets sent on the network. So it's a number crunching transaction system. The processor can handle 1 billion instructions per second. The disk can support 10,000 accesses per second, and the network can support 10,000 packets per second. How many transactions per second can the system support? Well, the majority will do a simulation, which is a very safe bet, so it's a good thing to do. A few people will do a queuing theory analysis. We'll talk about queuing theory in this course. This might be a more tricky to do, we will see. And some will do something else. Well, in fact, you might need to do all of this in reality. But the thing I want to explain here is what the something else could be. Because if we look here, for bottlenecks, bottleneck can be found for systems like this by looking at what's the load on the systems of interest. How far are they from their capacity? So this is captured by the utilization factor when we have a single resource here. So if I look at the CPU, one transaction costs 0.12% of the CPU, 1% of the disk, and 0.04% of the network. Therefore, there is a bottleneck here. That's the disk. Right? Because you have 8 times more usage of the disk. So in fact, what happens is when you do queuing theory, we will do that. There are complicated things that happen. It may be hard to know what exactly is the time it takes to do something. But we will see that in queuing theory, when we are at the limits of one thing being very lightly used or heavily used, then things become simple. And here one thing that is simple is that if we load the system by increasing the rate of transactions, the first thing that will happen is the disk will become congested. And when this happens, for example, when the disk has a utilization of 90%, the utilization of the processor will be 10%. So the processor will still be lightly used. So the performance will be dictated by the behavior of the queue to access the disk. So a very gross estimate will be, well, if I access the disk by 100%, I can never access it by, I can never use a resource more than 100%, a single resource. So the worst that could happen is if my transaction rate makes this 100%, which means 99 transactions per second. So if I go to 99 transactions per second, the disk utilization would go to 100%. We'll see that in queuing theory, a few bad things will happen before. You probably have seen that also. If you load a queue to 100%, the queue might go up, might congest. So probably we cannot go that much, but certainly that's a bound we cannot exceed. Right? So a very raw approximation of the capacity of the system is 99 transactions per second. Or at least that's an upper bound here. So if you want to say something about this, you could say, well, certainly it cannot support more than 100 transactions per second. We will see in the queuing theory part that there are systems in which we can make sense of this more mathematically and find a very, very quick evaluation of such systems. We skip this one. But there is another thing that may come. So the bottleneck is the thing that makes the analysis simple. As a first analysis, when the system has a bottleneck, we can ignore all the rest and model the system as simply the bottleneck. However, this does not always work. And the topic here is what we will do here. So here is something that some of you must be familiar with, but not everybody. That's a ring, a communication network, where some sources are sending data to a sink that is 2 hops away from them on the ring. Those are UDP sources. Why do I say UDP? What's specific about UDP? No retransmission, no congestion control. Here the point is no congestion control. So a UDP source does not adapt its sending rate to what happens in the network, as opposed to a TCP source. A TCP source receives acknowledgements and senses whether the acknowledgements are coming quickly. If they don't come quickly, the TCP source will not send quickly. So TCP adapts to the state of the network. UDP does not. With UDP, we just send, and it's up to the local system to throttle, put a rate. It's limited by whatever the system can do, or the access line, or whatever. It's always limited by something, but not by what happens in the network. That's also the model of the road system in most places. If you decide to go to Zurich today by car, you can look up on Google Maps and see the red road, but you can ignore that. There's nothing that will deter you from going there, even though I'm pretty sure now if you go to Zurich and in the afternoon, you will spend a miserable 2 hours stuck in jams all the way, but nobody will prevent you from doing it. Now assume that every source here is sending at a rate lambda, and what happens when the rate lambda increases? Then we can do the math that's given in the lecture notes. Those of you who took the TCP/IP course, you know this math. If I plot on the y-axis the throughput, the amount of data that goes at the end, what happens if lambda is very small, and I assume there is, at every node, there is one such source, so it's a perfectly rotation symmetric system. If lambda is small, there's no problem. What the capacity of the link is sufficient, and what gets out is what gets in. We are in this regime here. The output is y equal x is equal to the input. But problems start when we reach the capacity of the link here. In fact, every source uses 2 hops, so on one link there are 2 sources. There is this one and the previous one, which is not shown here. So if lambda reaches half of the link capacity, if lambda is the same in all sources, we start having a problem. We reach the capacity. When we reach a capacity, this is when performance becomes interesting, usually something will happen. Here what will happen is that as the first hop here comes, assume lambda is very large, much larger than half of the capacity. So that when it comes here, there is a huge amount of traffic that comes here from the other side, an even larger amount that comes here, so there is a huge amount of loss at the multiplexing point. So we will lose a lot of the data at the first hop. But some of the data will go there and will cause a loss of the other, and a loss of me too. So part of the data that I've sent here will be lost again at the second hop. And the result of that, if we do the math exactly, in that case it can be done, is it gives this monotonic effect, non-monotonic effect, that in fact what gets out decreases with what gets in, which is a completely paradoxical behavior. You have a system where, of course, it has a capacity. You expect if you try to put more things into it, of course, when it hits the capacity, there will not be more going out. But in fact, there will be less going out. Why is that happening? Well, this is because there is a waste of resource. Where is the waste of resource here? Can you put the finger on it? We keep dropping packet, but we could argue dropping is not bad. I mean, if I know a link has a capacity of 1 megabit per second, if I send 10, okay, I will get only 1 through it. Exactly. So what happens is some of the traffic that gets here is accepted on this link. So it is using the resources here. And in fact, because it's using the resources, it causes other sources to drop packet. But a fraction of this traffic which has used the resources will be killed at the second hop because there's another source that's coming here. So we've allocated the link capacity to some traffic, but later it will be killed. So we're using internal resources for units of work that will not complete. That's one of the ingredients that causes to what is called here congestion collapse. So this is called congestion collapse. Congestion is here, when we reach that point we have congestion. If the system would be well designed, the output would be this, would be the max. Right? How can we make the system well designed? Well, we need a mechanism to inform the sources that we should not send more, not more that one goes in the first hop, but not more that one goes at the end here, which is what TCP does. With this mechanism of acknowledgement, the source over time will discover that a lot of the things are lost on the way, so it will slow down and send only what works. So if we would use TCP, we would have a performance that would be, roughly speaking, like this. If we don't, we have congestion collapse here. So congestion collapse occurs when the cost per job increases with loads, or when, which is the case here, because every packet that is transmitted costs more, because in order to transmit one, we have to put more than one. That used some resources here. It occurs, for example, it's well known in information servers, in web servers. In a web server, when you have a transaction that comes, you have to use some resources. First, to do nothing. If you use TCP, it's just to do the handshake. But typically, you will also use TLS, so you need to start encryption. When you do all of that stuff, you still have not done any part of a transaction. Nothing has been done. Right? So in order to serve a transaction, there is a startup cost here. Now, what happens if a TCP server is receiving a huge number of requests? Then it might be that it's so busy just answering all those, trying to set up all those TLS connections, but it doesn't have enough resource for it. So it will try to set them up, but many of them will die. So there will be rejection of jobs before completion, or impatience. You click on a web page, some work gets done, but the web page doesn't come, you close the page and do something else. But the other server has done some work for you. So we have this pattern of impatience or lost job that does not complete, that all of those mechanisms cause congestion collapse. What do web servers do to avoid this? What would you do? Yeah. Limit the number of open connections. Yes, almost. In fact, what they do is they limit the resources that are dedicated to handling incoming connections with what is called a gatekeeper. So you have a job that has a limit on the CPU and memory that it can use that takes care of handling all this incoming connection. When this job is saturated, new connections cannot come in, but at least the ones that are in place, there is a minimal congestion decrease, but not a total collapse. The jobs that are present in the system will be able to do. So the take-home message is congestion collapse is very frequent. If you design a complex system, typically it won't come for free. So very sophisticated systems that have been worked out by a large crowd of people have seen and solved the problem of congestion collapse. The first web servers collapsed under congestion. The first version of TCP collapsed under congestion. Then people saw it and fixed it. So now if you install a modern system, it will have all the tools to avoid this. When you design your own system and you're the first doing it, look for such a pattern. It might well happen. It happens in the road system. Here, what is the ingredient that explains why this happens? It's called traffic jams. At the peak hour, the throughput of the highway between Geneva and Lausanne, which was less than the throughput at the off-peak hour, which is there are more cars, more people want to go to Geneva, and within an hour, fewer manage to get there. This is because when there is a traffic jam, well, the speed is very low, so the number of cars per unit of the road that goes through such a unit decreases. If we would find a way that cars can be very close together and there is no danger of doing that, it could improve things, but this does not happen. So, as a performance analysis job, you, depending on your system, you might have this pattern and you may want to look for it. Here is another similar but closely related thing. Sources here use TCP, so there is no congestion collapse. I have a red flow and a blue flow. This is normally the end, but I'll steal 2 minutes of the break to finish that, and then we will be done. The red flow has a certain rate here, right? So we look at the numbers. There's 100 kilobit per second available here, 1000 here, 110, 110. If there would be no TCP, there would be bad things happening because source 2 will send at full rate here. There will be lots of losses that will cause source 1 to suffer a lot of losses. But then loss 2 will anyhow have a lots of losses here because the rate is 10 kilobit per second. But if we use TCP, this will not happen. So if we use TCP, what will be the rate of the red source? It will be what will be the rates of the red and the blue sources with TCP, or with any system that tries to allocate rates in an intelligent way for this system. 10 for the blue. So I'm assuming we're not yet here. So assuming the capacity is 10 here, then the most that the blue can get is 10, and the most that the red can get is 100. So there's no point that they do more. They could do more because they don't know that the link capacity here. But if they know, the red will have 100 and the blue will get 10. Okay. So that's a common situation that illustrates complex systems where there is a mechanism, like TCP, to share the resources in a fair and efficient way. So because the system is susceptible to congestion collapse, we do something about it, and then we have a complex system. Now we change some of the parameters of the complex system. I upgrade the capacity here. What will happen to source 1? And the majority of you has found that we have this apparent paradox. Its rate decreases. Why? Well, because now source 2 is able to get more, and through the congestion control mechanism, we'll get more. So the fair share now will be that each of them will get half of the bottleneck now has moved. The bottleneck was this one, now it is this one. So each of them will get 55. So we have a combination of a competition and bottleneck. The bottleneck has changed, the competition is still there. So increasing capacity at one point may mean a decrease of capacity to one of the devices. So that's what we call competition side effect here. Now we can even do worse here. If I use UDP here, and if I had a link of 10 kilobit per second here, then we have by magic what congestion control would do. I've solved the problem by throttling the source. Right. If I remove this bottleneck, I will reveal a congestion collapse. So before, right, if we see the capacity of user 1 and the total capacity, when I increase the capacity of this guy, when I increase it, then I have congestion collapse because source 2 sends more, which creates a lot of losses, and the total throughput will decrease here. So we have another phenomenon that can occur in complex systems, that the system was susceptible to congestion collapse, and any system that is not protected by some special system protection mechanism is practically susceptible to congestion collapse. But there was, by nature, something that prevented it from happening. Right. But as we pretend to improve things, we remove a bottleneck somewhere, and then we reveal a congestion collapse. Many people are discovering that, so Switzerland is investing billions into upgrading the highway infrastructure, but the true bottleneck is in the city capacity, so we will create more congestion by adding more resource into the highway, but we will discover that in 15 to 20 years after spending a few billions on roads instead of research. So that's an apparent paradox of complex systems. Put more resources, all get less. In homework 1, what we have done is a very first homework that helps you focus on methodology. So there is no need to do your simulation. So it's the opposite of what you do in the other projects, where all the expertise is in doing your database system or your compression method for DNA structure or whatever. Here, we did it for you. So we have a simulator that produces the performance of Joe's shop. And there's a number of things that you can do. You can have access points, you can have base stations, you can have servers, etc. And we made a simulator that will that will give you some performance. But your job is to do the data analysis and analyze, using the scientific method, hopefully, what you can say about it. It's also an opportunity to learn about the standard tools in case you need. Voilà, that will be the homework 1. Homework 1 will be done, can be done anywhere on any machine. There is a session tomorrow from 2 to 4 o'clock in this room where we will help you with homework 1. But of course you can do it anywhere you want. And that's it for this session. We'll do a break now, a bit reduced. After the break, no lecture, but there is a set of questions that you can find on Moodle. And those questions, some of them are simply ticking a box, some others will take more time. And the idea is that you go through them at your own pace. We are here in the room. Whenever you need us, you ask a question. It will not be graded. You do it as you want. You can try as many times as you want. We're just here to ask questions, and we will make the solutions available tomorrow evening.